Anyway, I'll tell you something which doesn't have to be recorded, or maybe it is recorded. So you have a fuel and oxidizer which are initially separated, okay? And the fuel is coming from the top, the oxidizer on the bottom, and the dam color number is very large, is infinite. Remember the dam color number, it's a ratio, they say it's okay. Okay, didn't hear me. So remember that the dam color number, it's a ratio of the flow time to the chemical reaction time. So if the dam color number is infinite, the reaction is very fast. So a fuel element leaves here and an oxidizer leave here. Immediately as they meet, they react because infinitely fast. And so you expect the flame will be established and will touch from the edge on, from the tip of the plate, I should say, on. But in reality, the color number is never infinite. It could be large, but not infinite. And therefore, when the fuel and oxidizer come out, there will be some mixing that occurs. And therefore, there may be a premix flame established in this region where there is premixing of fuel and oxidizer. Now, I drew here only a segment of that flame. Further up here, there is more fuel than oxidizer. So that premix flame will be fuel rich on this side and will be fuel lean on this side. Now, if near the splitter plate, it's more or less close to stoichiometry. Now remember that lean and rich, the flame speed is maximum at stoichiometry and less on the fuel and lean side. So the flame propagates against the flow slower here than at the center, and so it will curve. And similarly, it will curve here. And so you're going to have a rich branch and a lean branch. Okay? Premixed. But there's a lot of fuel here. Some of it will go through unburned. And there is a lot of oxidizer here, some of which will go through unburned. So there will be a diffusion flame here that establish where they both meet. And so you're going to obtain a structure like this, which has an edge. It's not attached. And it's referred to as an edge flame in the literature. Sometimes they call it triple flame because it has three, but I don't like that term. But it is a term used. And sometimes it's called a tribrachial flame because it has 3 branches. And so it's 3-branch flame. So edge is pretty good term. Oh, I thought I turned those bright things in my face before. I don't know how to turn them now. Is that okay? Okay. So very often diffusion flames are lifted. They are lifted from the burner. And you want them to be sometime lifted because you don't want the flame to corrode the material of the burner and so on. And if they are lifted, there is a mixing region. This is not the true burner. I added that in the picture just for, illustration. But this flame was indeed lifted. And at the bottom, there is sort of this edge flame that I was talking about. Almost schematically, this comes from some calculation. you would have an edge here and an edge here and then a diffusion flame. And since this is a circular or a cylinder, then the flame, there's a symmetry and the flame reach the diffusion flame reaches the center. Otherwise, it extends down if it's a picture like this. So this is the lifted diffusion flame and the edge flame. Here is another picture of an edge flame that was created numerically by forcing a situation where the mixture is stratified. In other words, it's rich on one side, lean on the other side. In other words, not a diffusion flame necessarily, but stratified. And so again, you see there is a premix rich branch, a lean branch, and a diffusion flame that trails behind. Those branches can extend quite a bit or can be much shorter depending on the situation. It was really first observed or established by Phillips in 1965, and the idea was a model of what's happened in a coal mine where you have methane that tend to rise in at the roof of the mine, and it can cause an explosion under some condition. And so that was the attempt to understand what's going on. Another situation where these edge flame occur is when you have a hole in a diffusion flame, a turbulent diffusion flame, say, surface. So let's say you can see it here, for example, there is a hole in that surface. It's not connected, in other words, and you can see this is from an experiment. No, that's a computation, same as here. So you see there is a hole. In other words, there is a region where there is no burning. So it's a diffusion flame that there is extinction in that region. So now when there is extinction, since a diffusion flame separate fuel from oxidizer, in the hole they start mixing, right? They come from opposite end and start mixing. So they mix, so there will be an edge here, and that's the entire edge of that hole. Now that edge has some premix feature to it, like I described here. And so it can propagate. Premix flame propagate into the mixture. So it can propagate. So if it propagates in this direction, it will heal the hole. If it propagates in the opposite direction, which could happen depending on the situation, it extends the hole. It creates more and more of an extinction. So they are of interest also in turbulent combustion being responsible for extinction or reignition. It's not only in lifted diffusion flame that they may exist. They possibly could exist also in premixed flame, or at least some models that people have used to study these edge flame, or as I said, people call them triple flame. For example, here is two impinging jets, premix and premixed, and so you have, as we have seen earlier this week, twin premix flame. Now this is at least I'm showing you a mathematical description of an edge in this case. So this is a two-dimensional problem. So this flame extends in principle in the z direction, which is out of the wall or the board, all the way this way and that way, as well as the other one. In other words, there are two infinite planar surfaces, okay? But suppose that the condition here is that, and those are two flames, so the flame temperature is, say, the adiabatic temperature, right? But suppose that here now the temperature is cold, so the flame cannot extend all the way. So So it will have to end up somehow. And so it ends up by having a curved section that connects the two, and that's what I try to describe here. So on this end, it doesn't extend all the way, so it will curve and it will create again an edge. So this is another possible configuration to study edge flames. Experimentally, this kind of observation was done, for example, in a counterflow. Again, this extends all the way to infinity, so it will not have an edge. But what was done by Paul Roney at USC, he said, well, I'm going to have one of the two burners slanted a little bit, so they are not symmetric. So if they're not symmetric, then the strain rate is not the same all over. And if the strain rate at some end here is below the value for extinction that we saw earlier today, right? Strain rate, you increase the strain rate, you decrease the Dam color number, you cause extinction. So then again, you will create an edge. So there are different pictures of how it's created. I will focus on the mixing layer, which is perhaps not as simple mathematically as the last one, but it's one of interest, clearly. And so again, you have the two streams. You have the edge flame. This is a computed one, but stuck it here in the picture. You have a mixing region. So here is the premixed or the partially premixed of the fuel and oxidizer. This is the premix flame, rich, lean branch, and the diffusion flame trailing behind. This is basically what I just said on the blackboard a minute ago. In other words, if it was infinite, it will touch the wall, as we have seen in this example, it touch the burner, but otherwise it get lifted. So that I have already defined. So edge flame, I mean a flame that has an edge. Now, remember, the edge is not hanging out just like this. It's, of course, supported by a flow. So, in other words, the flame is sustained by this incoming flow. In most of the discussion or examples that I will show you, I will be using a constant density approximation. In other words, we are going to uncouple the flow from the combustion field. Otherwise, frankly, it's a difficult problem to do. If you want to do it completely, unless you cut some corners and do some simulation with those limits. So this is the picture. Saying that it's a constant density flow, early study have done the following. You say, okay, so we're going to put a uniform flow here and a uniform flow here. But that's not what I want to do. I want to actually compute the flow field in this mixing layer. So we're going to compute the flow by solving the Navier-Stokes equation, this region, something which has been done in the fluid mechanics literature in principle before, because it's a problem of interest even without combustion. And then once you have the flow field, I will use it. Again, it's a numerical tabulated result that I will use it to discuss the equation that you are already familiar with. It's the species equation, the energy equation, equation of state, and the reaction term. And I will be interested in discussing some aspect of this, like what's the effect of the overall flow rate on the flame, different velocities in the two streams, preferential diffusion of the different species, different than each other, and so on. Okay, now when I say previous study have compromised, the reason it's not a very straightforward problem, because I cannot prescribe condition at the splitter plate or at the tip of the splitter plate, the condition for the fuel and oxidizer. The equation are elliptic equation, the Navier-Stokes, and so you have upstream diffusion, okay? And if you have upstream diffusion, then you have really to solve the problem with some boundary condition far to the left, which is in principle at negative infinity. So in fact, you have an infinite problem to solve. And so that's why it's quite involved. So anyway, first let's talk about the flow field. So in the flow field in the wake of two merging streams roughly will look like this. The region, in this region, which is known as the near wake region, admits some similarity solution, and this is known from the 40s or 50s, I don't know, by Goldstein. It's not actually Goldstein's solution. And this is the nature, so you assume a similarity solution, meaning that the solution depends not only on x or on y separately, but on eta, which is y divided by x to the 1/3. And when you make that assumption, the Navier-Stokes equation end up into an ODE that depend on eta, and you can relatively easily solve it. And it describes properly the flow field in this region. The difficulty with this Goldstein solution, that it has a singularity at the tip of the plate. You see the transverse velocity v in this direction goes like x to the -1/3. So it goes to infinity. The failure is due to the fact that this equation assumes some kind of like a boundary layer approximation. And the reason it fails, it's because there is a small region near the tip where that scaling is inappropriate or fails, okay? It's we refer to as a singular perturbation behavior or singular perturbation. And so this is, by the way, this is what I am showing you now. It's the Goldstein solution. So it's just axial and the transverse velocity as a function of eta. Remember that eta is like y, essentially divided by x. So, and also something to note is that I have chosen two different streams, okay? So, and by the way, the condition, I didn't say that, the condition that this is solved even for that is essentially, this is like the boundary layer near the plate, okay, what you see here and here. So far away, it's the uniform flow. And so since we are in the vicinity of the tip, essentially the condition at negative infinity, which is far upstream in the plate, it's like the slope of this boundary layers, okay? But the slopes are in general different if you have two different streams. And the alpha coefficient indicate the ratio. So alpha equal to 1, meaning exactly same. Alpha equal to 0, meaning there is a stream only on the top, nothing in the bottom. In other words, if you are going to have eventually a flame, when I will put the flame in, the oxidizer is just entrained, but is not convected or does not come from a stream. Okay, so this is the picture, and so those are the solutions. So you see for alpha equal to 1, you get a symmetric solution, which is essentially what you have seen in the graph before, this part, right? Remember, eta is y. And for alpha equal to 0, you only have coming from the top, the bottom is entrained, as I said. Well, anyway, that's a detail. So what I was telling you is that where it fails in this close to the tip, and there you have to use the full Navier-Stokes equation. So if you are interested in the type of scaling that occur here, you remember that the boundary layer is on the order of the Reynolds number to the -1/2. And so the Navier-Stokes region, as I call it, compared to the boundary layer is another Reynolds number to the -1/2. So you can relate it to the length of the plate and so on. It's all fluid mechanics. Nothing that I have said here is sort of new, except that what we want is to solve the problem in this region, because we expect that the flame, at least for some velocity, will be established enough, close enough to the tip of the plate. And also, it's interesting that we have that solution far away, because the boundary condition, or at least not the boundary condition, but numerically what we anticipate is that the solution should tend, at least the velocity should tend to that solution far at infinity, okay? Which is important for matching the result to the proper solution. So anyway, this is the mathematical problem for the fluid equation, or for the Navier-Stokes. You can scale them in a certain way, where A is related to the slope here. In other words, in dimensional form, U equal to AY, and here is minus alpha AY. So if you scale with A, then it turned out that you get a problem that essentially is free of any parameter, and the beauty of this is that you can solve it once and for all, and then use that in a tabulated way to study the combustion. So this is just a general picture. Remember that I said, well, there is one parameter, which is alpha, but it comes from the boundary condition, from here and here. So remember I said alpha equal to 1 correspond to co-flowing stream. Alpha equal to 0 correspond to just flow stream of the fuel. Oxidizer is entrained, and anything in between is different streams. Okay. And so this is a picture of the flow field. When alpha equal to 1, you get streamlines as such. The flow that start mixing here accelerate and go towards the wake solution. And if alpha is not 1, you will get a picture which is as you expect. Here you have an entrainment. Alpha equal to 0 is a difficult case to do, so you do close enough to 0 and you get the picture of what's happening. So this is what the flow field will be if there is different streams. Now we want to focus on the combustion field. We know V, we calculated it before. We scaled the equation. And YFYO, it's like before, nothing new. I will use theta as my temperature by writing theta as T minus T naught divided by T stoichiometry minus T naught. So theta in the cold region upstream is 0. And so theta is deviation of the temperature. It's just, it's a simple way to rewrite the equation. And the phi here is the same phi that I have defined before. It's like a mixture strength, and we have, of course, Dam-Kohler number here, which is inversely proportional to A, which is related to the extent of the flow. So it's controlled by the flow rate. What else? That's what we have. Okay. Just by looking at the equation, if alpha is 1, the flow field is symmetric. If the Lewis numbers are 1, all the other equations are symmetric, and therefore, including if phi is 1, so then you expect a symmetric solution, right? In other words, it's going to be a symmetric picture around the axis. So here is a symmetric solution. What you see here is the edge, the diffusion flame that trail behind. Those are illustrated by reaction rate contour. In other words, omega equal to different constants. And when it's small enough, don't show it. And this is temperature field, so it's, of course, highest near the flame and decay as you go out. Okay, spread out. And these are the fuel and oxidizer mass fractions, so clearly one will diffuse into in this direction, the other direction, so it's quite obvious, and it's also symmetric. Here is a picture of a non-symmetric situation due to unequal strain rate. In other words, the two streams come with different velocities. Alpha not equal to 1. In fact, what is the alpha? Alpha is 0.1 in those. In this is the symmetric and this is the non-symmetric. So here, alpha is 0.1. So it's almost entraining oxidizer into the combustion field. And so you see that the edge is situated a little off the symmetric line. And also it's interesting to note that the fuel-rich end is a little longer than the fuel-lean. So the symmetry, the lack of symmetry is seen in various ways in the field. And you can see here also the temperature and the fuel and oxide. And by the way, note the upstream effect of diffusion. So it diffuses all the way to a certain distance away from the plate. And so that's a comment I made earlier. Here is a non-symmetric situation due to Lewis number. So here the Lewis number of the fuel is 1.8, of the oxidizer is 1. So in this case, the fuel diffuses at a slower rate than the oxidizer, right? Because the Lewis number is thermal to mass. So large Lewis number means a small diffusion of mass, small diffusion of fuel. So fuel diffuses at slower rate. And so if the fuel diffuses at a slow rate, the tendency will be for the flame to go towards essentially towards it, which is what you see here. It's not very significant, but it is somewhat. Here is the opposite direction, and you see that the edge is more situated in the oxidizer. So simply, it wants to see more oxidizer, and so it leans towards that. And this is a non-premixed, a non-symmetric situation due to, this is as I told you, I use that term, preferential diffusion. In other words, the fuel and oxidizer are different. Well, it's 1.8 and 1, so again, there is some effect of that. What does it imply? Diffusivity or mobility of the fuel is low. The oxidizer diffuses at a faster rate, and there are larger diffusion fluxes of oxidizer towards the diffusion flame that you can see here compared to here, or here compared to here, okay, which I try to show with the white arrow. And also the location of the diffusion flame and its edge vary. This is the mixture fraction Z. Those are constant line of mixture fraction. Note that the distribution is not very simple along one coordinate. And this is the stoichiometric value for the given condition, because you computed from 1 over 1 plus phi. So if the phi is specified here to be 1, then it gives you, about 1 over 2, so it's half. So the edge will always be located along this line. And when you increase the flow rate, it's going to move further away. Okay. And this is a non-symmetric edge, again, due to initial mixture. In other words, a very rich system, so there is plenty of fuel, so the flame tends towards the oxidizer. Okay. Now, I show all those, but really, I'm not sure where the interesting, there's another comment. There's some interesting things I want to point out, but they're coming. So those are just different way that the flame would behave according to this condition. But note here that this edge flame looks like a hook. In other words, the rich part is almost gone under this condition, again, because it's a very rich system, okay? And that's why I prefer to call them edge flame rather than triple, because there is no triple here, really. But anyway, that's how in the literature it happened. That's interesting because that also is consistent with what I showed you earlier, that unlike a premix flame where the flame temperature is always the adiabatic temperature, the diffusion flame, the flame temperature depend on the Lewis number. It can be above or below adiabatic. And what I am showing here is the temperature along the axis for a condition which it's non-unity Lewis number. LEF and LEO are equal, but not equal to 1. Since LEF and LEO are the same, then the picture is symmetric. Particularly phi is 1. I don't remember if that phi was 1 or not. But anyway, this is the temperature along the axis, okay? So it's the diffusion flame, which is along the axis. And what you see is that you get the adiabatic flame temperature eventually, right? This is the edge. The edge is a premix flame. So you have, first of all, a cold region, nothing. And then you have the preheat zone of the edge, right? And then the adiabatic temperature, the cold temperature, the high temperature behind in the burn region. Now, if the Lewis number are less than 1, you get super adiabatic flame, higher temperature here, and you get sub-adiabatic for Lewis number bigger than 1. Now, here is an interesting result that happened. What happened if you decrease the dam color number? In other words, you increase the flow rate into those streams. It depends on the Lewis number. So you see in this Lewis number, let's say 1, then you increase the flow rate. The flame, that's the location of the flame. You see it gets closer and closer to the plate, essentially. Slightly closer, but you get closer to the plate. And then there is a point here that it cannot get closer. This branch leans backward, and so it's unstable, can be proven. And therefore, that would correspond to an extinction point similar to the turning point of the S curve that I showed you before. Of course, here it's the position, so it's not the flame. Okay, so there is extinction that occur for Lewis number 1. But look what happened, Lewis number much bigger than 1. You increase the flow rate, the edge gets closer and closer to the plate. Then it comes to a point where if you keep on increasing the flow rate, it lifts off, it goes to higher and higher position. There is no extinction because there is no turning point. But I will show you also solution along those curves, and I will explain what is this dashed point. And then it keep on going, so it get lifted more and more and more, okay? Now, first let me explain what these are. Those are not the same as this. Those are dashed segment. This is dotted dashed. The dotted dashed is when the flame is in the wake. In other words, if we do the calculation, instead of using the Navier-Stokes solution, we use the Goldstein solution, which simplify, of course, the computation of because the flow speed is known almost analytically. Then that's the solution, which really blend into the Navier-Stokes solution when the flame is sufficiently far, because it has to go to the wake region. And so it's just a consistency of your calculation. This segment, I will show in a minute that it's unstable, and I would explain but what nature of the instability is. Let me just make sure that what I wrote here is all covered by what I say. So what I said is for low Lewis number like 1, but it's also true for other lower value, and I will probably show that soon. The edge is very close to the plate and is practically, maybe I should have put attached in quotation mark, it's practically attached to the splitter plate. And when you increase the velocity more and more, it get blown off by the flow and it extinct. It doesn't exist. The extinction here is get blown off. When the Lewis number is large, sufficiently large, the edge stands off the plate, get lifted more and more as the flow increases. Of course, it doesn't indefinitely. There will be a place where it gets blown off, but not described in this mathematical picture. So let's talk about that segment now. Oh, before we talk about that segment, here are pictures, similar pictures, but for different Lewis number. Note that for 0.8, again, you have this turning point and blown off here and here, whereas for this larger value, you have solution that show you a liftoff to higher and higher position. Experimental observations show that for light fuels like methane, ethane, the flame remain attached to the rim and is blown off when the flow rate exceeds some critical value. This was shown by Chung and Lee. And for heavier fuel like propane and butane, which is a larger Lewis number, the flame lifts off and stabilizes at a significantly larger distance from the rim when increasing the flow rate. I remember one day when Chung, I think his first name is So-Hoo Chung, anyway, is in Korea. He was at some point in Korea in KAUST. But he took a lighter, he designed it with a nice tip so that more or less you have a jet coming out, a nice jet. And for the large Lewis number, I don't know if you use propane or butane, whatever he did, he could ignite the flame and increase the velocity. What you do is the lighter, and the flame went up and up distances, as I'm showing you with my finger. I mean, quite significant from the burner. So it was a quite nice observation to see. And so that fits with this calculations, of course. I should say the calculation fits with the experiment. Now, what happened in this segment here? This part here, for the high Lewis number, which is larger and larger when you increase the Lewis number. So here is that segment. This is the solid part of the curve. So the flame is steady here and steady here, depending on the flow field, right? So what happened when I increase the flow field? Let's say, I don't know which one I started with. So, oh, here is A and here is I. So at A, if I perturb that state a little bit, see it's perturbed a little bit, eventually go back to the steady solution. So the flame will remain stabilized at that position. The position shown here, whatever it is, 95 or that. Same thing with I, is just that it takes maybe a little longer to happen. But in all these intermediate positions, we're going to see that the flame retain its position but oscillate. In other words, it's not blown off, but it's not steady. It oscillates. It remains oscillating. So you have a periodic solution that is retained. In this case, is a one frequency, multi-frequency, again one frequency, and those are all the intermediate points here. Of course, as it tends in this direction, the amplitude decreases to zero, and same thing there. And so there are essentially two modes of stabilization. The flame can get stabilized by the flow just by standing at a further position from the tip of the plate, or it can stand at a position by just oscillating but being there, okay? So two stabilization mechanisms. And here is, let's see. Here is this one, where is a single frequency oscillation. And this is the one with a two frequency oscillation at the points that I showed you before. Okay. One is interested also to talk possibly about edge speed, but I am not gonna, I want to just to minimize a little bit the discussion or to skip some things. So the idea is it's nice to have an idea how fast the edge propagate into the mixture. So there's been discussion on this. A comment about thermal expansion. There are very few calculations that we're able to do with variable density, in other words, not constant density. And what you see is, here is a picture where, of course, the streamline are deflected by the flame. Remember, this is a premix flame, and we have seen a couple of days ago that the flame get deflected towards the normal as it crosses the premix flame. And that's exactly what you see in these pictures here. This is for constant density, symmetric, and the flow is not. There is, by the way, two effects here. It's not shown in this picture. One effect is the premixed flame segment that you see, but also later in the diffusion flame, due to gas expansion, you get also a displacement, as we have talked about earlier today, of the counterflow. And that displaces in this direction, okay? So there are two effects, so it's richer in that sense. And finally, there was a discussion here. I will show only the pictures of the effects. So what happens if I put different plates, some plates which are, because you see some, now the flames stand off, but it can start heating the plate. So depending on the material of the plate, some of the heat conducted here go back to heat up the mixture, and that causes the flame to stand at a different direction. So if you are interested, you are going to see some of these effects discussed here. Okay, edge flame, other configuration. Oh, I just had one example. I think it's almost the last. A fuel and oxidizer coming at a corner, and so there's a nice mathematical solution without a flame that you can show, and with a flame you have to compute it numerically, and that's what you get. It's very similar to before, but the geometric picture is different. And so you have, again, an edge that stand at different position depending on the Lewis thumb. I think it's the last, at the end of the talk. Let's take a break and we come back